So today we're very happy to have Noah Miller, who's going to tell us about tree self-dual gravity, MHV amplitudes, and Lw1+infinity.
Thanks. Okay, thank you all for coming to this talk. So this will be based on two papers, one on the gravity MHV amplitude, another on Lw1+infinity, which hopefully will appear in the future. Okay, so as a bit of review, pure Einstein gravity at tree level, the amplitude for an arbitrary number of positive helicity gravitons to scatter is 0, all plus. If you add a single negative helicity graviton and a bunch of other positive helicity gravitons, the amplitude is still 0 at tree level. But if you add two negative helicity gravitons and the rest positive, the amplitude isn't 0 at tree level. And this is the so-called maximal helicity violating amplitude, or MHV amplitude, and it's called the simplest non-vanishing amplitude in Einstein gravity. So many of you may be familiar with the gluon MHV amplitude, which has a nice expression from the Park-Taylor formula. Here is the color ordered amplitude. So we have the amplitude will be the sum of traces of permutations of the algebra generators. And here's one such color ordered amplitude. And it's notably very simple. If you want to sum it, even say 5 or 6 loops, it'll be very complicated computation, many hundreds of diagrams, and it just simplifies down to this. So where does the simplicity of the Park-Taylor formula come from? Well, really see it as coming from the existence of self-dual Yang-Mills. So if we have the curvature 2 form for just Yang-Mills, if it's a self-dual, meaning the Hodge star of it is I times itself, such solutions are subsets of solutions to the classical Yang-Mills equations of motion, and any such self-dual Yang-Mills can be thought of as is an integrable sort of subset of Yang-Mills, and because it's so much simpler than Yang-Mills, you can sort of starting with self-dual Yang-Mills and building stuff on top of it. Stuff begins very simple and then gets gradually more and more complicated. But in this talk, we're not interested in self-dual Yang-Mills, we're talking about self-dual gravity. So what is self-dual gravity? Well, it's simply put any metric which satisfies the following equation. So if you think of the Riemann tensor as a curvature 2 form, if that is self-dual, then you say you have a self-dual metric. In particular, any metric that satisfies this equation immediately also satisfies the vacuum Einstein equations. In 1,3 signature, there are no real metrics that satisfy this equation aside from flat space. So metric perturbations on top of flat space will always have to be complex to satisfy this equation, although that won't be an issue for what we want to do with it. In 4,0 or 2,2 signature, the metric can be real. And self-dual gravity is the main object of study of twistor theory. We won't be talking about twistors, but I just wanted to point out that if you really want to study this in a very deep way, you should really probably be using twistor theory. Okay, but we're going to just use a simpler formulation of self-dual gravity. So for every self-dual metric, there always exists some coordinate system, which I'll call U, U bar, W, and W bar, where the metric takes the following form. So here we have the flat metric, and then here we have a perturbation on the flat metric, parameterized by a single scalar field phi. So where phi has to satisfy the following equation of motion. So this equation of motion, so here box is just the normal flat space wave operator, and this Poisson bracket is a space-time Poisson bracket just in two space-time coordinates U and W. So this funny equation of motion is called Blavatsky's second heavenly equation. And here U bar, W, and W bar in a 1,3 signature, you should really think of it in the following way. So these are like home coordinates. So here we have time minus Z and time plus Z. And here U and U bar actually real independent coordinates, but just for symmetry, I just kind of wanted to use U and U bar. But in 2, 2 signature, U and U bar would actually be conjugates to each other. Now, this is sort of a funny, form of the metric, but it's actually also a very natural form because this satisfies a nonlinear transverse traceless gauge equation exactly. So, so this is really a natural form of the metric to talk about scattering with. Just to be completely clear, there's only 1 degree of freedom here. This Kubanski scalar phi. This is really so. In general relativity, there's sort of two degrees of freedom, from the 2 velocities of the graviton. But here we've gotten rid of the negative velocity gravitons. Okay. So an exact solution to Kubanski's heavenly equation is where we just have phi equals some amplitude times the plane wave. And if you plug this phi into the metric above, you'll see that the metric is just exactly that of a right-handed gravitational field. So when phi is a plane wave, that's what a positive velocity graviton is. But because the equation of motion is nonlinear, if you want to take 2 gravitational waves and sum them, that won't be an exact solution to Kubanski's heavenly equation anymore. And this motivates the definition of a so-called Perturbiner expansion, which is a sort of funny name for actually a pretty natural concept. So a Perturbiner expansion is just some solution to some equation of motion where you have a sort of linear part that looks like a sum of plane waves, where each plane wave is multiplied by a tiny infinitesimal parameter. So here we have n plane waves 1 through n, and then the ith, and then here we have a bunch of epsilon i's, and each of these epsilon i's is infinitesimal and square root of 0, but the product of distinct epsilon i's isn't 0. So this is these epsilon i's are the stand-ins for these for this A we had earlier, this sort of amplitude for the plane wave, but here they're infinitesimal. And you should really think of these as gravitons. A graviton is a tiny gravitational wave. And the Perturbiner expansion will terminate at a highest order term of order epsilon 1 dot 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 epsilon n. So one could usually one would solve for a Perturbiner expansion using Feynman diagrams. And, this equation of motion has sort of a funny interaction term, but you can still use Feynman diagrams with it. They're not manifestly Lorentz invariant because we sort of singled out U and W, but in the end, anything you want to check, you check at the. So it's so simple that at the end you check that things are Lorentz invariant.
Is the claim that if you sum all the terms, you get an exact solution?
You get if you treat epsilon, with these rules of epsilon I, you get an exact solution. If you want to get a finite solution, you would have to say exponentiate the Perturbiner expansion. So you'd have to. This is sort of like adding in a particle should be thought of as an infinitesimal action on your space-time. And if you wanted to get an exact solution, you'd have to exponentiate.
Exponentiate in some nonlinear sense.
Yeah.
You don't literally just mean the exponential.
Right. I mean, the action of adding in a particle. Okay, so we're going to parameterize our momentum using a convenient choice of coordinates. So here, omega is some energy scale, and z and z bar are 2 stereographic coordinates on a sphere with a plane or what have you. And okay, we're going to define these. Okay, for simplicity, we're going to define these phi i's as these seed functions. So this is a seed function with its own epsilon and momentum. Okay, good. So what is the Perturbiner expansion just to the second order, just to with 2 particles? Let's start simple. So it turns out that sort of nicely, if you start with 2 seed functions, so phi 1 and phi 2, the whole Perturbiner expansion takes the following form. So 1 over z1 minus z2, and then the Poisson bracket of these 2 plane waves. So that's sort of suggested. Now, as an aside, there's also an analogous formulation of self-dual Yang-Mills So if you take the connection in these light cone coordinates, you can always write them using derivatives of this math frac, G valued scalar capital phi satisfying a very analogous equation motion. And if we define these are positive felicity gluons, if we define these plane waves, each with their own color and momentum, then it turns out that the Perturbiner expansion, you could use Feynman diagrams, or you could use this following formula, where from a sum of 1 to n, you take strings of length L, you sum L from 1 to n, then you take strings of length L, where the sort of letters of the string are 1 through n, and you sum all the color orderings here, and 1 over, the sort of string of adjacent, zij's. And this looks very similar to the Park-Taylor formula. And once you have this formula, you're sort of only a hop, skip, and a jump from the Park-Taylor formula. Although I'll just sort of point out they're the same. Anyway, the point is that you can take the Perturbiner expansion here and sum over color orderings. And this is a nicer, more useful expression of Feynman diagrams. So is there a similar expression for gravity? Okay, now we're sort of getting into the paper. So to the third order in seed functions here. So we have 3 seed functions, then we have the second order terms, but what's the third order term? So this is just maybe sort of an inspired guess, but let's just make a guess for this third order term. Let's take the second order term, which is this 1 over Z12 and then this Poisson bracket, and then let's insert into phi1 this combination of this sort of same combination of phi1 with phi3, and then we'll add into it a combination of phi2 with phi3. And sort of what maybe one motivation for this form, maybe this is sort of asynchronous, but this sort of looks kind of like an operator. This sort of has the flavor of an operator product expansion from conformal field theory, where and it's just a guess. For the fourth order term, you could do the same thing. You could take this third order term and then replace 1, 2, and 3, each with their own brackets between 4 and each individual particle. You get another term like this. Right, and these terms are given by binary tree graphs, which look a lot like Feynman diagrams, but they aren't. So notice that in the denominators here we have these z's. These aren't these are like zij's, not sij's. Where you would sum the momenta. So here I'm just showing progressively how you add in each individual thing. Okay, but these expansions, I'll just say that this is actually how you can solve the Perturbiner expansion, but they're kind of strange that they don't appear to be permutation symmetric. So this expression here is not symmetric between, let's say swapping particles, 3 and 2. It doesn't look symmetric. But let's define the differential symbol. Okay, partial mu and then I, where this partial mu I really is only supposed to act on the ith seed function. So you take a derivative of phi I and you get the derivative of phi I, but if you acted on phi j, you don't get anything. And let's further define this sort of Poisson bracket inspired object. That's sort of a Poisson bracket that only acts between seeds I and j. So I'm just saying that if you take this expression and you perform out just the product rule of differentiation. So here we take this Poisson bracket. And, okay, not expecting you to follow it all, but the point is that you can then rearrange all the terms and then in the end get something that is manifestly permutation symmetric between 1, 2, and 3. So in order to write out these Perturbiner expansions, let's define a sort of graphical element. So here we have a node I connected to a node j, and this corresponds to this this Dij over Zij operator acting on these two functions I and j. And for n equals 3, we can rewrite the Perturbiner expansion form. Oh yeah, so when I have this big phi and then these seed functions in there, that's my notation for the Perturbiner expansion of these seed functions. So we can rewrite all the terms in this n equals 3 Perturbiner expansion using these diagrams. So these single trees are just these initial seed functions here, and then here we have the second order terms, and here we have the third order terms. Okay, so that's for n equals 3. So now let's talk about general n. So let's denote Tn to denote the set of all marked connected tree graphs with n or fewer nodes, where each node has a distinct label contained in 1 through n. So, example, T9, here are some examples of graphs of T9 that nodes can have any number of possible connections. So, okay, so here's an example of how a graph translates into a term. So here's a tree graph, and for every leg, you add in for every leg connecting nodes I and j, you add in a dij over zij, and then you multiply, well, then they're all acting on the product of seed functions in the graph. So just to be totally clear, the general formula, so for any tree, for every edge in the graph, you act with this thing, and then you multiply by all the nodes in the tree. So the full Perturbiner expansion is then given by this formula. So just to be totally clear, the metric is parameterized by this Plebanski scalar. So knowing the Plebanski scalar is tantamount to knowing the metric. So this is an expression for the metric for any number of positive Felicity gravitons in space for space. Oh, yes.
Wait, sorry, is your Perturbiner expansion just Baron-Skiller?
Yeah,
I pronounce it. Is it equivalent? Because it seems like it's equivalent.
It's yes. So it's some.
Okay, but Baron-Skiller is equivalent to Feynman diagrams. So
Yeah, this
how
is equivalent to Feynman diagrams. I actually don't know this is certainly equivalent to Feynman diagrams. Although we're not using Feynman diagrams to write it. I don't actually know a direct proof of how to rearrange the Feynman diagrams to get this formula.
The Baron-Skiller type argument gives you that binary tree sum. And then you're using the sort of partial fractions of the 1 over zij's to get this other formula with your sum over trees. So that's the Baron-Skiller step.
Okay.
For your question.
But then, yeah.
But then your second formula doesn't look like the Baron-Skiller formula.
Yeah, the way
The original sum over trees is Baron-Skiller.
Yeah, that's the Baron-Skiller type solution to that equation.
Actually, I should ask you more about. So it was Baron-Skiller type. Is this
Yeah.
okay?
Yeah. Because it's isomorphic logic to Baron-Skiller.
I mean, I was, saw these formulas just trying to sort of generalize them. Wasn't totally sure. Anyway, although I'll say, okay, well, here, let me prove the tree expansion using a different sort of idea. So, well, okay, so you're not really supposed to give proofs and talks, but I'll just sort of give the proof and go through it, and then this will be done. But here's the proof of the tree expansion. So the proof works by taking the Perturbiner expansion and showing it satisfies this equation of motion. So recall here we have the box is the wave operator, and right here we have a Poisson bracket, and explicitly p dot x is this combination of u bar w bar. And so, so notably there's this, when you just take the exponential of this thing, if you take a u bar derivative of this seed function here, it's the same thing as taking a w derivative times minus z. If you take a w bar derivative, it's the same thing as a u derivative times minus zi. And so I'm just saying there's like a two-line bit of algebra that if you take the box of two seed functions, it ends using this formula here, it ends up being zij, dij acting on the two seed functions. Okay, it's then natural to define all these new graphical elements. So here you have the original one, and then we have the Poisson bracket of two seed functions. Just the dij acting on the seed functions, and then here I'll draw out the squiggly line and an arrow. And there needs to be an arrow here because this element isn't symmetric under interchanging I and j. So it gets a minus sign. So to account for the minus sign, you need an arrow there, and to have a box acting on these two seed functions, we're going to use a double line. So that's zij, dij. Notice that if you take this element here and multiply it by zij, you get this element, and you take this element and multiply it by another zij, and you get this element. So, for instance, if you act with the box or the Poisson bracket, you can use the product rule differentiation to expand everything out. So, for instance, if you have a box acting on these two seed functions, you sum over all of the pairs of seed functions that act with zij, dij. As this. So, for the product rule differentiation, that implies the following thing. So, yeah, the box on the seed function, you're summing over all placements of the double edge going between two nodes in a graph. And we'll call all such graphs that are constructed by taking a graph and adding a double node Tn box. And then for this combination here with the Poisson brackets, partial u, partial w. So because of the Poisson bracket, this is sort of one wiggly line going from one graph to another, but then the extra partial u, partial w then becomes a second wiggly line connecting the two graphs. So to evaluate this sort of thing, you need two graphs and you have a wiggly line from one to the other. And because the epsilon ij's all square to 0, these two graphs will have distinct nodes. So here's an example. So here we have a graph in T9 box. So we take a pre-existing tree graph and we add a double line. Then here we have a graph in TPT29, where we have two pre-existing graphs with no shared nodes, and then we draw two wiggly lines between them. Okay, so note that both these graphs contain a single cycle in them. And using the rule earlier where I said you could replace these lines, multiply them by zij, you go from here to here and then here to here. So if we single out a group of graphs that all look the same, they have a cycle except for the placement of the double line. If we then sum over the placement of the double line in the cycle, we can just say that this sum of graphs is equal to this graph, where we sum over all the zij's in the cycle. So this sum of graphs is equal to this graph times this zij. And similarly for this sum of graphs, we have we have two wiggly lines in the cycle. So you have to sum over all placements of the two wiggly lines. And if you do that, what you get is a sum over all pairs of, all distinct pairs of edges in this cycle. So here we have the graph without the wiggly lines, this sort of all sum of pairs. And then our proof will be done if we can show that sort of this graph equals this graph. So it's just this factor that we have to show is the same. But the equivalence of these two graphs just follows from squaring this following thing, which is 0. So if you have a cycle of zi's and you sum all the zij's in that cycle, you get 0. And then if you square this thing, just FOIL that out on, you'll get on one side all the squares and on all the pairs. And this logic works for cycle of any size, and that completes the proof. So that's actually the only way I specifically know how to solve this exact equation. Anyway, so that's the proof of the tree formula. Okay, so what do these trees have to do with MHV amplitudes, which is in the title at the top? So, one element multiplicity formula for the Graviton MHV amplitude was written down by NSVW, Nguyen, Spradlin, Volovich, and Wen in 2009. So if we scatter n+2 gravitons with the minus gravitons, labeled by I and j. So here I'm just defining the integer I to be n+1 and the integer j to be n+2, and that's going to label the negative helicity gravitons. In the MHV formula can be written as a sum over trees just of the positive helicity gravitons. So here so just the positive felicity gravitons get a tree, and then you sum over all the trees with and elements and take this particular combination, and that's the MHV amplitude. And in our formalism, in our particular parameterization, we can take ij to be zij and this bracket to be this combination. So another very related formula is Hodge's formula, which you might be more familiar with, which is you write the MHV amplitude as it's a kind of determinant of a matrix. And this is equivalent to the NSVW formula using the combinatorial matrix tree theorem, where the computation of the determinant-like object can be rewritten as a sum over trees. Anyway, so formulas like the NSVW formula, you don't prove these formulas by reorganizing Feynman diagrams because that's prohibitively difficult. Instead, how historically Feynman is the authors NSVW wrote down the formula and they just checked it was true using BCFW recursion. One may wonder how the amplitude could be computed directly, just using general relativity, as in you don't have the formula ahead of time and check it's true, like can you build up the formula? So this was accomplished for the first time in 2021 by the authors Affiliation and Sharma using twistor theory. They're using their nonlinear twistor sigma model to calculate the formula. So second, we've read a second proof, not using the CFW recursion or twistor theory, but instead just using Lubansky's second heavenly equation. So yeah, so the Behrens-Gila thing, I don't think there's any, well, there isn't a known way to get this particular version of the amplitude using Behrens-Gila. So that's sort of not known. Like there's another formula, the old-fashioned EGK formula, that's understood, but this thing isn't understood in Behrens-Gila terms. That would be interesting. But okay, any case. So right, so okay, how does this proof work? So well, once you sort of have the metric of the positive felicity gravitons, you sort of solved half the battle. So both this proof and the Mason-Sharma proof, well, on a basic level, they work by computing an on-shell gravitational action for a self-dual spacetime, where you then add two anti-self-dual perturbations. So if you have a self-dual metric made up of a bunch of positive felicity gravitons, if you then add in two negative felicity gravitons, now you get a spacetime corresponding to the MHV process. So I just want to remind everyone what the connection between amplitudes and classical solutions. So how do you take a classical solution and get out an amplitude? So okay, here's a scattering amplitude. So I don't know, just for simplicity, picture in your mind, maybe you have, phi cube theory or something, doesn't really matter. Okay, so we'll use a convention where the incoming momentum will have a positive energy and the outgoing momentum will have a negative energy. And one could imagine a classical solution where you start with some sort of sum of plane waves, then progressively solve to higher orders with your interaction term, which would be higher orders in A as well. So in the free theory, you can always define these coherent states just using exponentials of the creation and annihilation operators. And the coherent state path integral turns, so if you want to compute some sort of S matrix element of coherent states, what it ends up turning out is that the positive and negative frequency parts specify your initial and final data. So the positive frequency part specifies your initial data, and the negative frequency part specifies your final data. So this is a sort of a mixed boundary condition path integral where you're specifying different stuff in past and future. And in the future, you have a sum of future plane waves. In the past, you have a sum of past plane waves. Now, if you want to take tree level amplitudes, you want to find classical saddles, so these boundary conditions. And so to get a normal scattering amplitude of just quanta, not coherent states, you then just differentiate everything by all these well, okay, you're using the word amplitude in two different ways, but the amplitude of the waves, not the amplitude of the event, but you differentiate by the amplitude of the waves on this thing here to get the tree level amplitude. You differentiate by these A's here, and these get you the normal in and out states from a normal scattering amplitude. And then if you just want the connected part of the amplitude, that turns out to not e to the IS, but just IS itself. So then we can think about making the substitution of AIs to what we call the epsilon I's previously, so I'm just going to do that. So, and here is the connection between scattering amplitudes and on-shell actions, where when we take this limit that the epsilon I's are to be evaluated at 0, that's sort of why we sort of use this prescription where we take this sum of plane waves and then we solve progressively. So that's sort of where this prescription comes from. So, okay, so there's a convenient trick for calculating MHV amplitudes using classical actions. So for going gravity, let me just explain the basic strategy using Yang-Mills. So here's the standard Yang-Mills action. You can then add in a topological term that doesn't affect the scattering amplitudes. And if you separate out the connection, or sorry, the curvature into self-dual, anti-self-dual parts, you can then show that this thing is just, well, it only depends on the anti-self-dual part of the curvature. So on a self-dual background, the anti-self-dual part of the curvature is 0. This is the defining equation for self-dual Yang-Mills. But then if you add in an anti-self-dual gluon to a linear order, you're now going to have a non-zero anti-self-dual part. So if you add in two, so see, it takes two anti-self-dual gluons to make this action non-zero. And we want to use this formula to calculate the amplitude. And unless you sort of have two independent anti-self-dual gluons, this thing won't be non-zero. And this strategy was used to compute the Park-Taylor amplitude using perturbiners and self-dual Yang-Mills by Slivanov and Rosley in 1998. So in some sense, this paper is sort of doing what they did for Yang-Mills, but for gravity. Okay, so now, okay, good. So I'll just sort of briefly say, like, what's the analogous formulation of Einstein gravity? Well, that turns out to be given by this Plebanski action. Where, here, RAB is the anti-self-dual part of the Riemann curvature 2 form, and gamma AB is the anti-self-dual part of the spin connection 1 form. These sigmas are the basis of 3 anti-self-dual 2 forms, and they're made out of these tetrad 1 forms. So here I'm using this little a is the flat space Vierby indices, then capital A and capital A dot are the 2 spin indices, toggle between Pauli matrices. Anyway, this is even though this is explicitly written in terms of purely self-dual sort of variables or anti-self-dual variables, it's actually an action for full Einstein gravity. Actually, this action is literally equal to just the integral of the curvature scalar, and therefore vanishes on shell. But it turns out the correct action to use is you have to sort of integrate. You have to sort of integrate by parts here. So take this d and put it here, and it differs by a boundary term. That turns out to actually be the action you want to use. It's not. Okay. Anyway, if you plug in the equation of motion, the action simplifies for a situation where you have a self-dual background and 2 anti-self-dual perturbations. And it turns out that the amplitude is just given by the following formula, where here we've just rewritten the action on shell. So to reiterate, these little gammas are the perturbations of the anti-self-dual part of the spin connection. So these things can be set to 0 in a self-dual background, but now this is like, these are kind of like the F minuses. Oh, yeah, sorry.
Sorry, one more question. You just said that the correct action differs from the previous action, which gave 0 only by a boundary term.
Yeah.
So that all of these things are coming from a boundary term in flat space.
Sort of has to be that way in gravity. talk more about that after. Okay. Okay, so I've talked a lot about the self-dual perturbations, but okay, how to add in the anti-self-dual perturbations. So I'll just sort of outline generally what the idea is. So you can always decompose the Riemann tensor using using the sort of anti-self-dual part, self-dual part, in Penrose scalars. And it turns out that on a self-dual background, this anti-self-dual part is 0, but a linear perturbation, which we use the little letter psi, you sort of rearrange the Bianchi identity, and you can show that the equation, I should have equals, but the equation of motion for this thing, for this anti-self-dual, anti-self-dual perturbation, is actually just the linearization of the normal Polanski second Hedley equation. So for instance, if you wanted to compute this object here, psi ABCD, so let's say you have two self-dual gravitons and you're adding one anti-self-dual graviton, you would just sum over all the tree graphs that like only contain your new graviton in it. So if you start with 2 and then add in a third, it's just the ones with in it. So I'm just sort of laying out like the general strategy. And then once you know this anti-self-dual curvature, you then can solve for the spin connection. They're related in this way, which is just the norm, which is just the linearization of the normals of a standard form. But in any case, this is actually sort of the complicated part of the proof, and solving for the spin connections and dealing with that is the main complication. But anyway, the point is that the objects can all be, I've sort of explained to you how the objects can all be computed, and then you can find this sort of action, and you sort of write in different ways, and you need to use different nodes, and you use the wiggly nodes, and the wiggly edges, and you need to define some different nodes, and you need to manipulate them with rules very similar to the rules I was showing you earlier. So the graphs you're summing over look like this, and long story short, you sort of can Frankenstein together the MHV amplitude using this action, and you get out the NSVW formula. Actually, the formula you get is a new slight generalization of the NSVW formula. So with some extra reference spinners added in, and it actually turns out to be a sum over graphs where you include the negative helicity gravitons too. So these are included in the graph, and there's sort of reference spinners that connect them to the rest of the graph. So, and for some particular value of these reference spinners, recover the NSVW formula. But it's sort of interesting that you can get trees where you also have the negative helicity gravitons in there as well. I don't know uses, but anyway. Okay, so
This dependence on the reference spinners disappears in the final formula.
yeah, you can show that formula doesn't depend on them, then you take them to particular values and they go away and you get the NSVW formula. Okay, so you're not supposed to not usually supposed to give proofs and talks, and you're not supposed to change what you're talking about in the last 20 minutes of the talk, but I'm just going to do that anyway. So let me tell you a bit about Lw1+infinity, which was actually how I got into this. So, okay, anyway, so Lw1+infinity symmetry is a sort of, and by the way, I'm not a twister theorist, so I don't want to give that impression. I don't actually understand a lot of this stuff super well, but okay. Anyway, the point is that it's a symmetry, it's a manifest symmetry in twistor space that's well, you deform the complex structure of twistor space, and then that affects your metric and your self-dual metric in some way. So, okay, so just what's the abstract definition of the W1+infinity algebra? So this is the W1+infinity algebra is the name of an algebra that everyone's very familiar with. So it's just literally it's just literally functions in a two-dimensional Poisson bracket. So here you have a Poisson bracket in U and W, and you can define these generators that are just polynomials in U and W. And okay, we're taking with integer exponents, labeling in a funny way, but whatever. Here I'm labeling the generators as such, and you just literally take these generators, put them in the Poisson bracket, get out a commutator. That's the W1+infinity algebra. You can then loopify any Lie algebra to get, well, you can loopify any Lie algebra, and you can also loopify this Lie algebra to get the Lw1+infinity Lie algebra. So to loopify the Lie algebra, you sort of add in an extra integer to the generators, and then the integers add to, you just sort of define this new commutator. We just kind of add integers together. And I'm sorry that the notation isn't, well, couldn't really do much, but there's 3.5 W's in this, on this thing. So there's this W here, there's this W, there's this half frac W, and then U is half of the W. So unfortunately, there's 3.5 W's. So what do the Lw1+infinity transformations do to a self-dual space? Right, so this was really the instigator. So sort of telling the story backwards. There are these symmetries that affect twistor space in some way, but how do you just act them on metric? That was sort of the question I was originally interested in. And what these transformations do is they correspond to adding in a self-dual graviton with a very specific wave function. So here we have the phase space of self-dual metric. So you start at the middle with the flat metric where phi is 0. Then you add in well, a self-dual graviton with a particular wave function, you sort of go away from it. And if you add in one and another, and then another, and then one, the order in which you add these things does matter, and the commutator between them is exactly the Lw1+infinity commutator. And so then the question becomes, okay, you don't want to always just work around here. You want to work around some other point. So how do you get from here to here? Is there a way to like recursively get to the like nth perturbation away from flat space? And the answer is yes, using a Perturbiner expansion. So the wave functions we use are the so-called conformal primary wave functions used in celestial holography. So we have these wave functions that are parameterized by conformal weight delta, and then z and z bar. And you can act on these wave functions using the Lorentz generators, which you can split into SL2 plus SL2. And you can use these generators to take descendants in z and z bar. So you can sort of start with these conformal primary wave functions, which depend on an angle on the two sphere. And okay, ignore this factor out front here. The important thing is you can trade this bar for some integer n bar by taking progressive descendants in n bar, and then you could then finish off by getting a full descendant in both z and z bar by then taking descendants in z, L minus 1. And good. So the half descendants in particular, if you actually just write out what the function actually is, they're exactly these polynomials in u and w, but they're sort of like shifted by z. Right, so these are exactly the W1+infinity algebra polynomials shifted by z. And so that implies that if you have sort of these two wave functions at the same, so they can have different deltas and different n bars, but if you take them at the same z and take the Poisson bracket of them, they satisfy the W1+infinity algebra.
Sorry, can I just ask, goes a little fast. So the W1+infinity algebra, that's the algebra of Poisson diffeomorphism on C, on C. I'm just confused, where is the loop? So you talked about the loop algebra of W.
I haven't fully gotten to that part.
Okay, but that's because you're gonna eventually go on CP1 as opposed to C or something.
I'm not worrying too much about what's complex and what's not, other than just declaring what's complex. And you'll see where the loop comes in very quickly. Right. But anyway, I'm just pointing out that just as wave functions, you put the wave functions into these two wave functions at the same z, satisfying the W1+infinity.
Could you remind us what the half descendant is?
Yeah, it's just you take this conformal primary wave function and you can, so they're sort of parameterized by two angles on the sphere, z and z bar. You take descendants just for this, so you trade the z bar for an integer n bar just by taking descendants. You set z bar to 0, and then you take these Lorentz. So these are just the space-time Lorentz generators. You take these Lagrange generators. So you can start from Z and Z bar, and the half descendants, or you just trade the Z bar for the N bar by taking, you're just Taylor expanding in Z bar, and you can Taylor expand in both of them to get these. So, okay, so now let's not use the plane wave seed functions, but let's use seed functions that are these sort of half descendants. Then we still actually have this formula. Nicely enough. So this is actually how I mean, actually, so the way I got into this was I wanted a formula for acting in Lw1+infinity on self-dual spacetimes, and I was thinking, okay, I want to find some way to add in these like half descendants, and Feynman diagrams don't really work for that because you have to integrate over energy and stuff. So I'm like, okay, I want a nice formula just for adding the half descendants, and just sort of tried a bunch of things and came back, with these trees, and I'm like, these trees something? And I asked someone, and they said, oh, those trees are in the MHV form. Okay, should probably do something with that then. But now we're sort of back at the original intent of my what I was interested in. Okay, so if we have a Klebanski scalar, which we have a bunch of seed functions, these half descendant seed functions, we can then define a linear perturbation to this metric by just adding in an extra seed function here. So here I'm sort of taking this list of seed functions, then denoting this bar, then an extra seed function to just be like the linear change in the Perturbiner expansion when you added an extra seed function. So I'm just defining this to be the change in, let's say, this Perturbiner expansion. You then take this half descendant seed function, you add it in, and then you integrate it around all the other seed functions, and you weight this integral by 1 over zi, where zi is the coordinate of your new seed function you're adding in. You integrate that around all the other seed functions, and then you that to the ni plus 1, where ni is the ni that's in this sort of added seed function phi I. So now we're seeing where the loop is coming in. So the commutator, there's action just from the standard contour pulling trick using 2D CFT. So we have this tree expansion formula that lets you solve for everything, but we also have the binary tree formula, which sort of shows you the leading term as two zi's get close together. So you take two zi's close together here, and then you get the additional, it's just the Perturbiner expansion where you add an additional function, but this additional function here is 1 over zij to the Poisson bracket of two seed functions. That's what I was saying. At the same z, they satisfy the W1+infinity algebra. And so just using this argument here, we just immediately can show that you can add in these wave functions, and these are indeed the wave functions that give you that give you the Lw1+infinity commutator on the spacetime. So, any questions about this? This is where the Lw1+infinity comes in. This is just like spacetime. Okay, so I'm almost done, but the last thing I like to say is how these Lw1+infinity transformations, how well-known set of diffeomorphisms called BMS transformations fit within the story, or rather extended BMS. So in Bondi coordinates, which I'll just write as capital U, capital R, capital Z bar, and capital Z, there exists a set of vector fields called super translations and super rotations, denoted by CF and CY. So F is just a function on the sphere. The super translations are sphere-dependent translations, and the Y and Y bars are holomorphic and anti-holomorphic function on the sphere. These are local conformal transformations on the sphere. And the form doesn't matter. I just wanted to show that these are just space-time vector fields that the super translations are parameterized by function f, super rotations are parameterized by vector field y. So a diffeomorphism then acts on a metric using this standard formula. But you can think of this, the Lie derivative acting on a metric is sort of a perturbation to the metric. We can also think of this perturbation another way. We can think of it as, you sort of add in this thing here, this seed function to the metric. And then if you then want to like consistently, let's say, solve some equations of motion, you would then find that you actually needed the second. So if you started with a solution and then you added this other seed function in, you'd have to then solve the next order term. And then then after that, you'd be done. You wouldn't, like the thing would terminate after that, but adding in the seed function. So turns out that for a certain subset of these seed functions here, the tree formula reproduces this Lie derivative acting on the metric formula. So it ends up working out quite nicely, but I'll just sort of say that you're really adding in a pure diffeomorphism seed function. So if you're thinking about these seed functions as particles, you have like, let's say, a complete basis of particles, some of those particles are going to be pure gauge particles. And I'll just say that, so you'll have a pure diffeomorphism seed function, then there'll be all of the graphs for this pure diffeomorphism attaches once to the tree. So this first thing is this first thing here, then where it attaches once, that ends up reproducing the next order correction. And then whenever the pure diffeomorphism seed attaches to two or more nodes on a tree, those just end up evaluating to 0. So within the tree formula, you can see its action. And I'll just sort of say that, so if you're the W generators, I'm just sort of a certain subset of the W generators are a certain subset of super translations and super rotations. So in particular, we have these two infinite strings of super translations. So for instance, the 4 constant translations, the Poincare translations, just in the 4 space-time directions, those are in here, as long as many others, as well as the anti-holomorphic conformal transformations on the 2-sphere. Those set of, a subset of BMS transformations you can see read easily in here. But these formulas, can also be generalized. These vector fields, here I took particular deltas, 1 and 0, but you can take any delta and 2 more infinite towers of diffeomorphisms beyond just BMS, but for delta, the BMS are just 2 rungs. Okay, so we're almost at the end, almost out of time. So just to recap, we discussed 2 things. We discussed a perturbiner expansion for self-dual gravity. We discussed just how one writes a metric with an arbitrary number of gravitons in it. That's a very basic thing to want to do. Could come in handy. And we showed that we could use it to provide you could build up the MHV graviton formula. The trees in that formula are sort of imprinted in the trees, the trees in self-dual gravity sort of imprint themselves on the trees and the Graviton MHV formula. And we also discussed how we could use the Perturbiner expansion to talk about Lw1+infinity transformations. But I've sort of used the Perturbiner expansion to do 2 things to talk about Lw1+infinity and MHV. But one would like sort of powerful relation between these transformations and MHV amplitudes. So is there such a thing? It's kind of all suggestive. There's the sort of OPE like cursive formula. Maybe there's some sort of current algebra that you could use to compute the Graviton MHV amplitude. So such a current algebra was identified by Nair in 1988 to compute the Yang-Mills MHV amplitude. So that's intimately connected with the twistor string and the CSW formulas and for Yang-Mills. So if you could do that so there's a lot of stuff you can do for Yang-Mills with MHV amplitudes that you can't do with gravity. So, if you could start doing some of these things, that would be interesting. That's the end of my talk. Thank you.
Are there more questions? No?
Yes,
There's something I can understand intuitively. So self-toy angles is interval, so it doesn't produce scattering. And that's supposed to be the reason that the all pulse amplitude is zero. But all pulse amplitude is, this way speaking, it means all pulse coming in and all minus coming in. But mindfully self-toy angles is all talking about scattering which pulse modes. So it's like it's pulse going in and pulse going out. I'm sure I'm thinking about it wrong, but I can't quite see what the mistake is.
I think, yeah, just to when you outgoing, you just have to think about everything being starred here. So that all the, well, if you have the, right, so if you have the creation, so the creation annihilation operators, you take the sort of Klein-Gordon inner product and you put in a solution into them. And to get out, you know, what creation versus annihilation operator sort of has an implicit star in this wave function you put in. And that star acts on the polarization vectors, and so the outgoing things. So if they're all minus, that's still self-doing.
Well, I'm still confused, but I'm sure what you said is correct.
Any other questions? If not, let's thank Noah again.